Okay, so here's my problem. I've written out the information for this particular situation. We have rectangular domain. The specified temperatures are just provided some, TH and T infinity are certain values. We'll say H bar is 30, conductivity is 10, and heat flux is 1,000. Those are all the things we needed to set up the boundary conditions. Okay, so what we do now is we want to solve for lambda times W for the ith one of those. So lambda times W indexed at I. So this is just that equation that I wrote before. It's minus K lambda W over H bar times W is equal to tan lambda W. Right? That's the equation we had. Notice that I'm creating this variable lambda W. It's a single variable. That helps us specify bounds on that variable rather than having to specify bounds just on lambda. Because we know the product, we know that the lambda times W has that nice periodicity. It's related to the pi over 2 or whatever, where lambda is going to be a lot more messy by itself. The scales by W. Okay, so we have this equation. And our job now is to find the value lambda W that satisfies that equation for all the different values of I that we want to plot out. Okay, so if we were just to go in here and provide a guess for lambda W, solve it, it would find one value. That's not good enough. So what we want to do is we're actually going to compute the lower limit. So here's our lower limit. Here's our upper limit. I guess I'm using this domain. It's probably right. I'm just overthinking at the moment. So let's assume the lower limit and upper limit are what we say here. Right? This is the domain that we can find the solution in. So I'll call this lower limit upper limit, and I'm doing it for every single value or index I. Okay, then I'm going to provide a guess value. Let's say just right in the middle of those two limits. Okay, so how does this help? This is all in the equations window, and guesses are provided somewhere else. Right? So let's go to the guess or the function information. Right, that is, it's F9, but it's which one here? I'll just hit F9. Okay, F9. Okay, so this is where you go in and provide the initial guesses. Let's not show all the array variables, like every single index. Let's just show the variables as they appear. Okay, so here we see everything is kind of its default, except this lambda W. So it turns out ease has this nice function where you can come in here and specify guess value, limit, a lower limit and upper limit using other array variables that are of the same dimension. Okay, so it's a little hard to see, but I'm saying lambda W, which is brackets, it's an array. The guess value for that is the guess thing I calculated right here in the equation window, which is the midpoint of the lower and upper limit. Then lower limit's the lower limit, upper limit's the upper limit. So when it solves this, it's going to kind of iteratively update the guess values and limits and actually determine what the lambdas are. Let's do this. So solve it. It's solved. So now if I look at my arrays window, all right, I see lower limit is updating according to that formula I gave, as is upper limit. The guess is right in the middle. And now lambda is solving for each of those different cases. Okay, that's kind of a cool feature, I guess. So now we've actually identified all of our eigenvalues, or our eigenvalues times W, basically. So that's how you do that. And actually, you're gonna need to do this, I think, for the homework for this week. So yeah, if you have any questions on that process. No? Okay. Again, these files are all online if you need to refer back to them. Okay. So we've now got our lambda values from ease. Assuming we're going to continue to solve this problem in ease, we would just take them. If let's say you wanted to solve this in MATLAB, probably the best thing to do would be figure out how many lambda values you're going to need, compute them in ease, maybe then just copy them into a table or an array or something and put them in MATLAB. That's one way to do it. There's also root finding things in MATLAB you can use, but we won't go into that right now. Okay, so we've got our lambda values from ease. So let's move to the next step. And again, just a little short on time to go through all this, so I just have it written out for you. So what we want to do then is solve the non-homogeneous problem for every eigenvalue. We've solved the homogeneous problem. We've gotten the eigenvalues out of that process. Now we need to go back and apply this. Since we've come up with a bunch of lambda i's, we have to go back and do the same thing for the non-homogeneous problem. Okay, so here's our ODE. Right, again, we're saying it's minus because this is the non-homogeneous direction. This is our eigencondition, and we've now used this to solve for our eigenvalues. So what's the solution to this ODE? Well, it's sinh and cosh. Right? Sinh and cosh times some unknown constants, and we have I of those solutions, so we have to put the index I on them. Okay, so same thing we did last time, sinh and cosh. Oh, incidentally, in Maple, so let's say you get a solution, and Maple gives you back a solution for this problem that's exponentials. There's a function in Maple, and I'm saying this, I can't remember. It's called, I think it's called convert. I'll confirm this, but you write the expression, right? This is your, whatever the thing you want to convert. Like, let's say this here was in terms of exponentials. So you'd write the expression there that you want to convert, and then there's different like keywords that you can use to convert from one thing to another. So we would convert this to trig. So you actually just write trig as it is there, no quotes or anything. And it'll take that exponentials and find an equivalent hyperbolic formulation for it. Okay. So at least when I solved the homework problem for this coming week, I had to do that. I just want to make a note of it. And I'm 99% sure it's convert. I'll correct that if it's not the case. Okay, so we have our hyperbolics ready to go here. Step 5, determine the temperature of the solution for each eigenvalue. That means we're bringing everything back together. Okay, we bring back together theta x, theta y, multiply them. This is our theta x here, sine, and then here's our theta y. We bring the unknown coefficients into the equation, so we are left with basically two sets of unknown coefficients, infinitely many of them. And then we assemble all the solutions, meaning all the I solutions become or come together to form a single theta solution. Yeah. So let's see, C1 of I was up here. So we were left with this expression, like this is our solution for theta x. C1 I is then, comes up because we have lambda i's. When we combine this equation, that solution here with our solution here, we would have had here C1 I in front of that, but an unknown constant times an unknown constant is an unknown constant. So we just, it sort of absorbed by the others. Okay, so we assemble all the solutions, and we have now our full kind of final general solution in terms of theta here. Okay, same thing we did last time. So let's wrap up this, and then we'll get to the actual superposition part on Monday, I think. Okay, so step 7 is enforce the boundary conditions in the non-homogeneous. This is again going to follow pretty much the same procedure, except we have a slight difference which we need to go through. So we're taking now these two things. So we have boundary condition 1, boundary condition 2 in the y direction, and we need to enforce these. All right. So let's do boundary condition 1. So this becomes q dot double prime is equal to minus k times the sum from I equals 1 to infinity of sine lambda I x times C3. Let's see, what do we have here? Lambda I times sinh of lambda I times 0 plus C4 I lambda I cosh of lambda I 0. Okay. Evaluate this out, and it becomes q dot double prime is equal to minus k times the sum for I equals 1 to infinity of sine lambda I times x times C4I times lambda I. Okay, so again, now we're left in a situation where we have C4I unknown, or infinitely many of those unknowns, and we have this function of x appearing in this boundary condition. And now you should have an idea where to go with this, right? We have a function of x. We need to get rid of that function of x in order to solve for the constants. How do we get rid of it? Use orthogonality. So we use orthogonality, and we're going to multiply both sides of this equation by our eigenfunction, which is orthogonal to this series. Okay, so to do that, we say q dot double prime times the integral from 0 to w, x equals 0 to w, of sine lambda I times x dx. Okay, right, that's our eigenfunction there, is equal to minus k c4I lambda I integral from 0 to w of, on the right hand side we have sine lambda x, so that becomes sine squared of lambda I x dx. Okay, so we can evaluate this, go to Maple or whatever, do the integrals. Well, you know, okay, sine the integral of that. We probably could know the integral of sine squared, but you come up with a determinate answer. It's a definite integral. We're going to get an answer that's no longer a function of x. We've integrated away the x part of the equation. Okay, so let's just assume we do that. We apply the orthogonality, get our equation. Now we have an equation for every C4I. Okay, but let's look back at our second boundary condition. Okay, sorry, I know I'm at 11. Give me about 30 seconds here. So our second boundary condition is this up here, right? And if we enforce that, we end up with the following. So sum sine lambda I x C3j times cosh, sorry, is that j? It's I. C3I times cosh lambda I times h plus C4I sinh lambda I times h is equal to th minus t infinity. So, okay, we have a problem, right? And our problem is we still have a function of x, and now we have C3 appearing again. Right? It just showed up again. So what you have to do again is apply orthogonality one more time. Okay, so we apply orthogonality and solve using that new equation. Now we've got two equations, two sets of unknowns, and we can solve both of them. Okay.